Has anyone started the homework, by the way? Other than Emily? She's almost done with it already. Anyone? You have. Good. All right. I'm going to say that this is 5 kips per foot. Let's say that this is 5 feet. And I'm going to give you guys a vertical force of 15 kips here. Uh, 4 feet and then 4 feet. And what I want you guys to do, just really quickly, draw the shear and bending moment diagrams. Determine what the reactions are. Yep. And now that I think of it, let me be right back. I'm going to go grab the textbook. Also, Joseph, did you send it through your Suffolk email or personal? Because depending on which one you send it to.
It might have been personal because I don't know if I switched it or not.
Yeah, so if it's through personal, yeah. So be careful when you're sending it.
No, that makes sense.
All right. Freeze these screens. Oh wait, I just realized. You guys technically already have the design tables. Yeah. They're all in your packets right here. Yes. Nice. about 3 more minutes. Tres minutos. Saw a lot of interesting answers. Doesn't mean it's a good sign. It's interesting in the sense that you just killed probably 1,000 people. Figure it out, Nicole?
No.
You want to go over? Just giving up. Minute before the time's due. All right. Let's go over it. Who here thinks they got it? You think you got it. Okay. Where did everyone get up to? Everyone should have solved for the reactions. Did everyone do that? Everyone got the reactions they needed? All right. Did everyone at least draw the shear force diagrams? No? Some of you? Who here got to the bending moment diagrams? Nobody. All right. So that gives me an idea on who watched the lecture last class. So I'm just going to draw a horizontal line. That's going to be my placeholder for the shear force diagram. All right. So first step, we don't have the reactions, so we got to solve for equilibrium. External equilibrium. So take some of the moments. Let's call this point A, point B, and we take the moment about point A. You could take it about point B. My recommendation is just always work with the furthest left point. That's my recommendation. It just makes life easier for me anyways. All right. We are going to have 5 kips per foot times 5 feet. And this is the magnitude of this distributed load here. And then its location with respect to A is 5 feet divided by 2. So take that 5 feet divided by 2. And then lastly, this is going to be a negative moment because it is causing a clockwise rotation about point A. From here, you add By, because By is its own vertical force, and Ay. And By is 9 feet away from the supports. And then lastly, you have the 15 kip force multiplied by its perpendicular distance of 13 feet. Solving for this, you should get By is 14.72 kips moving upwards. Everyone got that? Hope so. From here, you do sum of the forces in the y direction equals 0. You have negative 5 kips per foot times 5 feet plus Ay plus 14.72 plus 15 and you should get that AY is equal to negative 4.72 kips, which indicates it's going downwards. So now we go straight to our shear force diagram. We learned previously last week, just follow tip to tail. So our first force is going to be the 4.72 kips. We determined is going downwards. So bring that down 4.72. From here, we need to compute the next shear point. Let's call it V1. And this is just going to be the negative 4.72 minus the 5 kips per foot times the 5 feet it's distributed over. Which means that our second shear point is negative 29.72 kips. And that is going to be roughly here. All right, how's it going to look? Is it a straight line? Is it quadratic? What do you guys think? It's a slope down. So, it's just a straight line down. Where do we go from here? Where's the next interesting point? It's going to be at BY. There's no load applied in this area whatsoever. So because of that, it's a straight line across. And this value is negative 29.72. I'm actually going to remove that negative sign and just indicate negative here. Next, we take V2, and that's going to be the negative 29.72 kips. And we have to add BY, which is 14.72 kips. Which gives us negative 15 kips exactly. So we pull this up. That brings us over to here, roughly speaking. And then there's no force applied until the point load at the end. So what this means is our beam is basically subjected to negative shear the entire time. Are there any questions about how this was obtained at all? This height here was that BY, which is 14.72 kips. Oops. Next step, we have to draw the bending moment diagram. Whoops, straight lines only. Now, what is the bending moment? Hold on, actually, let me double check something. Yeah.
Shouldn't BY be negative?
I think you're right. Let me check. Negative 5 times 5 times 5 over 2 plus 15 times 3 multiplied by negative 1 divided by 9. What do you get for BY?
For BY, I have the same number, it's just I have it negative.
Yeah. You're right. Which means that this is going to be negative. That is negative. Yeah, because I was just thinking it, because you can kind of see the shear force diagram closes out to 0, but at that point, it's going to mess up your bending moment diagram, because it's going to tell you that it's not going to close out to 0, because if you're just summing negative moment the entire time, it's not going to close out to 0 at the end. So that's a good point. So that means negative 5 times 5 minus 14.72 plus 15 times negative 1, which means that this reaction, what do you get for AY? Is it 24.72?
Yeah.
All right, so then that's technically downwards, and that's upwards. All right, first mistake of the semester. All right, so attempt number 2, I'm just gonna draw this really quickly. We go up 24.72. Then we compute the first shear point, so 24.72 minus 5 times 5. So 24.72 minus 25 is just going to be negative 0.28. So it brings us to a really small value. That point is going to be like roughly here. Connect tip to tail. And then there's going to be no shear at all up until BY. Then V2 is just going to be negative 0.28 minus 14.72, which conveniently gives us the negative 15. All right, that makes more sense to me, much more sense. Just label your values, negative 0.28, and then negative 15, with this being a height of 14.72. All right, now to draw the bending moment diagram, we need to basically take the area of each of the shapes, and as we move further left to right, we'll find moments for different points. All right? The first step is we need to find the area of that blue triangle. There's just one issue, and it's that you need to account for the fact that it is transitioning from positive to negative here. We'll call this dimension A. We can find A pretty straightforward. You just take the relationship of 24.72 divided by A and set that equal to the magnitude of the distributed load. This comes from similar triangles, or law of sines. If you really want to do the law of sines, it's up to you. So for A, what you should find is 4.944 feet. And so from here, when we're calculating the first bending moment, you take the area of the blue triangle. The area of the triangle is 1/2 24.72 kips times 4.944 kip feet. And that gives us a bending moment of around 61.11 kip feet. That's going to put us somewhere up here. Where this value will be aligned as such. How's it going to look from our start point? How's it going to look?
It's gonna be
Concave up or down?
This way. Up, I guess.
This way? Yes. Good. It's going to look just like that with a bending moment of 61.11 kips. Kip feet, sorry. Make sure your units are right. From here, you calculate the next bending moment. That is going to be the bending moment at that point there. It seems small, so it's relatively negligible, but this dimension is just going to be 5 minus A. Which is 0.056 feet. So M2 is just going to equal the 61.11 kip feet plus 1/2 times the negative 0.28 kips times the 0.056 feet. And what you'll find is a slight decrease from the 61.11. About 61.10 kip feet. So there's really no change. Very small. From here, calculate M3. And this is just going to be the 61.10 plus the negative 0.28 times its length, which the length from here to here is exactly 4 feet. This gives us 59.98 kip feet, which very small again, but the important thing to note is that it is linear. So this was quadratic along with that, but this here is linear. From here, you just calculate your last point. So you take the 59.98 and just add negative 15 times 4 feet. With some round off error, clearly, it's going to be approximately 0. So our numbers are right. It's just with all of the rounding off that we kind of did, the numbers don't close out perfectly. Otherwise, if you had kept the exact numbers, it would have closed out. So as long as you're like 0.01 kip, 0.02 kips, that's not going to make a big difference in the diagram. When it starts coming into play is when you're like 5, 10, 15, 20 kips off. Does that make sense? Good. Let's do another one really quickly. Oops. So I'll say that this was another example. This is, again, another example. Let me look at my notes. Let me find one in the textbook. That's what I feel like doing. problems are like too annoying. I don't really want to deal with them. Yeah, this one should be good. Got a pin here, a roller here, a distributed load along the full length of the beam with a magnitude of 1 kip per foot. And then you have a vertical force of 8 kips located a distance of 8 feet from the left-hand support. And the total length of this beam is 40 feet. Firstly, find the reaction forces. We'll call this AY. And BY. And then draw your shear and moment diagrams. And you guys should be able to do this by 7 o'clock. So in about 15 minutes, you guys should have both diagrams. Everyone almost done? 5 minutes left. Yes. Sure. What's your vertical reactions on the right hand side? 21.6. Yeah, so this should be continually going down. You probably just what is so 26.4 minus 32 gives you 13.6. 1 kid per foot times 40 feet minus 8 feet. So that's 32 feet.
But it goes all the way to the end.
Right, but here's a point. So all of this, if you cut in section, this is 32 feet worth, and then it drops and then continues dropping down. It's following tip to tail. So you're gonna have a vertical force, it's gonna continually decrease, and then there's gonna be an immediate drop here because of this 8 kit force. And so then after that, it's gonna continue to go down until it hits this point here, and then it's gonna shoot up to 0.
So then that must be Romans or?
Probably, yeah, since your shear force diagram is a drop right. Yes. Yeah.
Just BY 40, right?
Yeah. BY would just be 40.
So then, would this be positive or negative?
Well, your reaction is wrong because you're forgetting the negative sign here. Because this is also causing a negative rotation down there.
Oh, so this whole thing is negative, right?
That should be negative, yeah. So your reaction is wrong. Yes.
I'm stuck on this part
Okay.
where I was stuck last time too. So I got there with this, and then I got there with this, and then I kind of subtracted.
And you got 54 that?
Yeah, but then I divided it by 2, right?
Nope. Oh, yes, yes, because it's a triangle.
Yeah, and then where do I go? What would I do from here then?
You would generally separate this into a triangle
Yeah,
and a
okay.
square. Otherwise, my recommendation is, what is that shear right there, that point?
Negative 18.4.
All right, so take the average between those 2 points and then multiply it by whatever spin length this is, because that'll give you the same.
Okay, and then I just add that together.
Add that to the existing moment that you calculated for that point.
And then I subtract it.
Yep, and it should close out to 0 if you did it right.
Okay.
All right. All right. Where'd everyone get to? Why is this? Come on. There we go. All right. Let's go over it. First step, static equilibrium. Sum of the moments about point A equals 0. We have the 1 kip per foot distributed load over 40 feet, and its center is halfway along the distributed load, which is just going to be 40 feet divided by 2. And you multiply it by negative because it's causing a negative rotation about point A. And then you add the negative 8 kips times 40 feet minus 8, which is 32 feet, plus by times 40 feet. Solving for this, you should get by is equal to 24 kips. Everyone get that? From here, you do sum of the forces in the y direction equals 0. Negative 1 kip per foot times 40 feet minus 8 kips plus AY plus 24. Solving for AY, you should get 21 kips. Everyone get that? Okay. And both forces are moving upwards. Let me just double check the values just to be sure. Oh, that's because I gave you guys the wrong value for the force. All right, so I am going to improvise it then because the force was supposed to be 5 kips in the textbook, but I'm an idiot who can't read. So this value is 26.4 kips, which in turn means -1 times 40 minus 8 plus 26.4. 21.6 kips. Did everyone get that? Everyone should have gotten that now. That is my bad. In the textbook, this number was 5 kips. So that's where I went wrong. All right. From here, we draw our shear force and bending moment diagrams. Start out with the shear force diagram. All right. And follow tip to tail. AY goes up 21.6. From here, you calculate the shear at various points. Our next point of interest, we'll call V1, is going to be where this point load is. So this is just going to be 21.6 kips minus 1 kip per foot times 32 feet. Which should give us -10.4 kips. that puts us somewhere around here. I'm actually going to move that slightly over. So from there, you draw a line. Whoops. Make it a straight line because it's a linear distribution. Positive and negative. From here, calculate the next point, V2, which is just going to be negative 10.4, and account for the 8 kip force, negative 18.4 kips. So that drops by about 8 kips, bringing us to negative 18.4. And then shear 3 is just going to be the negative 18.4 minus 1 kip per foot times 8 feet, which should give us negative 26.4, which should be equal and opposite to the reaction. Because when we add the reaction, it'll close out to 0. And that is your shear force diagram. Did everyone get that? Good. Now, for the bending moment diagram. What we need to do, again, take the areas. What do we notice here? We notice that there's a point crossing 0 in between 2 points of interest. So what we need to do is determine where this location is. Let's call this location A. Take 21.6 kips, divide it by A, and this is going to equal, hold on, 21.6 plus, equal to the magnitude of the distributed load. So pretty straightforward. A has to be 21.6 feet. Before I continue, does anyone have any questions about anything that I'm doing so far? Am I going too fast? Everyone following along? All right. So, first moment is just going to be the area under that blue triangle. 1/2 times 21.6 times A, which is 21.6 feet, which gives us a bending moment of 233.28 kip feet. How does this look? Linear, quadratic? Quadratic. Concave up or down?
Concave down. Like this, right?
Yes, that is concave down. I like how I asked concave down and versus concave up, and I don't even know the difference. So, yes. Looks just like that. And then, just so you guys don't have to write out the equation, just indicate that it's a quadratic distribution. Especially since during an exam, you guys might be rushing, so just make sure you write quadratic or linear if you're not clearly drawing it properly, just because it at least helps me understand your thought process. From here, M2 is just equal to the existing bending moment, and then you subtract that additional area, which this area from here to this point is going to be 32 minus A, which is 10.4. So 10.4 kips times 10.4 feet. Which gives us a bending moment of 179.2 kip feet. Which puts us down here. So that's 233.28 and then 179.2. And then lastly, calculate M3, which is just 179.2 minus, there's two ways you can do this. You can break it up into a square and a triangle, or you could just take the average of the max and the min because it'll give you the same area. So what that will look like is negative 18, minus, or yeah, plus negative 18.4 plus negative 26.4 divided by 2, multiplied then by the length that it spans, 8 feet. And that equals 0. And how does this look? Again, it should be quadratic. And that is your bending moment diagram. Really quickly, looking at this diagram, what bending moment would you use to design for? What would be your design bending moment? If you were to design a beam, we are going to be covering this after the break, but I just want to ask you guys, what's the maximum bending moment in this beam?
Moment 1.
Which is 233.28, right? Now, for the design of the shear forces, what shear force would you use in the design?
26, 21, 26, good.
Wrong. 26.4. Because all the negative does is just tell you which direction it's traveling. So because of that, the 26.4 kip force is actually going to be the governing in the design. Make sense? Great. I'll give you guys about 5 minutes. Let's try and come back at like 7:20, no later than 7:25, and then we'll go into an introduction in beam design. It's not too difficult, fortunately. I just shocked myself. Yes. I have no idea. I just touched this and I saw a spark. And now? All right, no worries. Just watch the rest of the lecture.
Yeah. Well, go ahead.
Have a good one.
I was gonna test it, we have 2 more, correct?
There are 2 more.
Yeah.
And next test is gonna be entirely on beams, and then the last test is the miscellaneous stuff, which
So that
is
would be like the.
torsion and column buckling.
But I feel like it's fairly predictable.
Column buckling is honestly an easy topic until you start adding more stuff to it.
Like in terms of what?
Accounting for the correct, the thing with column buckling is understanding the boundary conditions for the problem. And then also understanding how different, for example, alright, this column right here, you might think it's just, okay, whatever the height of from this floor here to that floor here is, but it's not as simple as that, because that column spans several floors.
And then the other size of the stuff too, it changes as it goes up, right?
Yep, and then accounting for the stiffnesses of the beams too, which we don't really get into. I give you guys very simplified models.
I was gonna say like OTP and composites when it comes to that or not?
With composites, you can.
I was gonna say, cause you had the steel and you have, I'm sure there's some type of W shape inside of it or something like that.
Nope, not usually. Usually, like this is a masonry column, so because of that, it's probably just gonna be just the C&E blocks that you see with the concrete infill, with the grout infill, and then probably like some type of like number 4 rebar with stirrups surrounding it.
Yeah, I think it's some information. I'll take 2 scissors. I don't know about one. Instead of. What, 3? There's that no way that you don't know. But what do you know of? Okay, you're Jewish, and what else?
I'm trying to remember. It's like so broad.
What's very broad?
Like ancient history.
Oh.
I tried to take an
You're
answer.
definitely like mostly German.
Irish.
And Irish?
Mm-hmm.
Are you both or just one?
Mostly Irish, actually.
Really?
Mm-hmm.
Dude, I'm like the opposite. I'm like mostly German with a touch of Irish. So it's pretty.
How far did you go with your building design? Yeah.
Interior walls, I didn't get as far as I was hoping for, honestly.
I'm at doors and windows.
That's what I want them to be at, but I didn't get to it.
I'm gonna do it tomorrow.
Yeah,
It's really easy.
yeah.
Who needs windows? They're a pain in the butt to design.
No,
I want it done by this weekend, though.
Yeah, no, me too. It's really easy. I'm not
Yeah.
gonna- Are you taking that next semester?
What?
Presentation?
Yeah. I might do. I don't think next semester. I can do my drafting by this year.
Did you make your
I know
schedule
that's
yet?
drafting, but like I think my. Huh?
Did you make your schedule?
Yeah, I just have to type in the thing like. I opened up with it.
Oh, okay.
I have all my ceremonies. So I'll load myself on 5 classes one day.
I'm gonna be here Tuesday, Thursdays only.
So like.
You're actually gonna do that?
Yeah. It's not even that bad. It's like 8 in the morning to like 5:45. It's a normal 9 to 5. It's nothing.
Yeah.
And then the one class I meet once every other week, so it's like. Oh, new formulas. It's still warm.
Yeah, right off the printing.
Oh, yeah, man. At least you stapled them this time.
What?
At least you stapled them this time.
Yeah.
Yeah.
This doesn't mean that you guys don't need to know shear and bending moment diagrams, but these, for design purposes, will help speed up the process. Like if I give you guys a simple beam to design, alright, because sometimes with beams, they can be a long, strenuous process. Especially if you have to draw the shear force and bending moment diagrams, and then with some of the beam properties that I will be covering today, it's going to be a simple pick and choose off of the tables. But in a lot of cases, if you're doing something like a built-up member, you've got to do the calculations for the second moment areas of inertia, as well as the first moment areas of inertia. You guys remember that from statics? IX, IY.
That wasn't that bad. It was tricky in the beginning, because I used to not have stuff pretty bad.
Yeah.
But then I got it.
Now, do that on top of having to draw these shear and bending moment diagrams. It makes the problems extremely long, which is why if I give you guys something like a built-up section to analyze, it will be with a loading case from those tables explicitly, at least for an example, because otherwise you guys will be there all day trying to do one problem. Make sense? And then I'm gonna get your packet in a second. All right. All right, so the packets I provided you guys are shear and bending moment diagram packets. Are basically this packet, it's a supplemental piece of, did I give somebody my own packet? Oh, crap. Whoops. Oh, well. I think I gave somebody else my packet. What? Nope. I've got it right here. This is my own packet. All right. So, I'm not going to go straight into the packets right now, but when we're doing example problems, we'll be using it. So, now what I want to go into is just an introduction to beam design. All right. Thank you for letting me know that. I would have gotten halfway through the lecture and yeah. Oh, by the way, everyone vote today. Express your First Amendment rights.
No.
Nah?
Voting's stressful, man.
What?
Voting's stressful, man.
Voting's stressful.
And I also got into the whole, like, politics is, like, not a good thing in my house, because everybody's so, like,
Diversified in
yeah.
it.
So
Mm.
it's just, like, it's not even worth it. It's just a screaming match.
All right. Introduction to beam design. Now, when it comes to beam design, let me just actually really quickly draw like a simple diagram. We have a beam here, and it's resting on some type of support, and let's say it's got some point load located here. How is the beam going to deform? We know that the beam is going to deform kind of like this, right? Do you guys agree with me? We call this deflection. We'll get into that later on in the semester. But this is generally how it deforms. Now, one of the important things to note is what the stresses look like in this beam. So, I'm going to ask you guys something. Are the stresses going to be the same on the top and the bottom? No. What's going to be different, Michael?
I'm not sure.
So the top is going to compress.
Oh, you mean like that? Yeah.
Yeah. So the top of the beam is going to be undergoing compression, while the bottom of the beam is going to be undergoing tension. This is one of the reasons why in reinforced concrete beams we use reinforcing bars, because the concrete itself cannot handle any tension. So the tension needs to be carried by the steel. Now, how does the stress distribution look? We need to take a cross-section view, and I am going to just draw a line downwards just like that. And let's say that this is a section view. We'll call this AA. I'm going to move this over just a schmid. And let's say that this cross-section just is something rectangular, very simple. All right. The way that the stresses will look are as follows. We will have a compressive stress up on the top, and then a tensile stress down at the bottom. Now, how does this vary? It varies linearly between the two. We'll call this sigma t, and then we'll call, oh wait, this is sigma t, and then this is sigma c, which is negative and positive compression, or negative and positive forces, or stresses. But you guys notice that there is a point in this beam that isn't stressed at all. You guys learned that this is called the neutral axis. Does that term sound familiar to anyone? Well, hopefully when we do a quick example for this rectangle, let's say that this has dimensions of 8 inches and I don't know. Actually, not 8 inches. Let's say it's 2 inches and 8 inches, nominal. All right? Now, how would we find where the center, there? You guys remember that if you had a general shape, right, and it wasn't something as simple as a rectangle, one of the things that you would need to do is firstly find off where the center of the shape is, which we called this Y bar. You guys remember what Y bar is? It's the location to the center of the cross section, which is actually what we call the neutral axis. So that neutral axis you can take with respect to the top or the bottom. Basically, it's wherever the center of that shape was. If I were to instead change this to something more along the lines of a built-up section, just like this, hold on. Then this Y bar would be slightly higher, right? You guys agree with me or disagree with me on that?
I agree.
Yeah. And so then what happens is these stresses kind of shift proportionally, where this kind of decreases in value. But to compensate, this would increase in value. So you can have stresses that vary from the top or bottom. All right, but let's keep it straight up to my regular example here. So, when you are solving problems that aren't as simple as this rectangular shape, one of the things that you would need to do is compute what your Ix is, as well as your Y bar. This Ix value, what is Ix for a rectangular shape?
Like the formula?
Yeah.
EH cubed over 12.
And so if you plug it into the calculator, what do you guys get for Ix? What you guys get? Michael, what'd you get?
85.33.
All right. And where's the neutral axis going to be? Anyone? Four inches. All right. Now, that begs the question, where does all of this come into play? Now, there is a giant derivation that I can really do involving the analysis of the stresses and so on and so forth. I am just going to entirely skip that for you guys, so that way I am not boring the hell out of you, because the math is a little bit aggravating. But what you guys do need to know is the bending stress, where the stress felt in the beam is equal to M times Y divided by I. So, Y, however, we're going to call this just arbitrary y. This is different from y bar. Y is basically your coordinate position from the neutral axis. Right? So here, if you wanted to find the stress at the neutral axis, this value y here would be what? It's the distance from the neutral axis. If we wanted to find the stress at the neutral axis, how far away would we put it for y? The answer would be 0, because we're analyzing it at the neutral axis, so there's no offset distance. Does that make sense? Now, if we wanted to find the maximum stresses that we feel, well, there are two ways to do it. Well, one way, but just for compression and tension. If you wanted to find the maximum compression force, you would take whatever the bending moment is in the beam, multiply it by YC, and then divide it by I. Now, if you wanted to find the stress and tension, it would be the same thing, but just repeated. Now, why do I say I instead of IX or IY? It's because I is just generally denoting the orientation in which bending is occurring. So for this problem, is bending occurring about the IX orientation or IY orientation? IX. What if bending was occurring about the IY orientation? How would the beam look in that case?
It would be flipped the other way.
Not flipped, but it would be rotated. Where the 2-inch part would be basically the height of the beam. And then you would stand on top of it, so it would flex a lot more, right? Does that make sense? So I is just a general notation. So that's simply it. I don't even think we really needed this. I'll leave it. But yeah. So one last, yes.
Will we have to be able to tell if it's IX or IY?
Yes. Yeah. One of the ways that's pretty easy to tell is with like W shapes. So if I had given you guys a beam and it was loaded like this, but if you were to basically look at it from a cross-section view, right, you would see that the load is either going to look like option 1 or option 2 for a W shape. In this case, you would use IY, and then in this case, you would use IX. Does that make sense? And the reason being is because those are the values that are tabulated on the tables here, which you can manually calculate those. It's just reverting back to your statics for calculating IX and IY. Does that make sense? All right. Now, there's one more step that we can really take to simplify the calculations. When we have symmetric shapes, YC and YT are always going to be equal, right? Because the neutral axis is just at the center of the beam. So we just default it by saying that YC equals YT. Then the ratio of I over Y, we set this equal to what we call a term S. This is the section modulus. Simply put, for a rectangular cross-section, we know that y bar was equal to h over 2. Ix was equal to bh cubed over 12. So when you do the math and set I over y, you would get bh squared over 6. That's it for a rectangular shape. For more complicated shapes, like a W shape, you would need to consider the depth of the beam, divide it by 2, take the second moment area of inertia. Does that make sense? So for a W, you would just take whatever the depth of your beam is, divide it by 2, because that'll give you the height of half the beam, right? And then you take your second moment area of inertia of that entire beam and just divide it by half the height of the beam, or half the depth of the beam. Fortunately for you guys, many of your design tables have already done this for you and given you guys the values in terms of SX and SY here. So just understand what your orientation of the beam is and you will be good. Take a minute and just take a look at those. Yes. Rx and Ry are your radius of gyration. Those come more into play when you're dealing with column buckling, but Rx and Ry is equal to the square root of the second moment area of inertia divided by A. So you don't really need to know that right now, but I guess for your own reference, R is equal to the square root of I over A. Just a good note to have. All right. So for symmetric shapes, you can use sigma is equal to m over s for your calculations. Else use sigma is equal to my over I. All right, the best thing that we can do now is I am just going to throw an example at you guys. Now, let's take this beam that we previously had. All right, so looking at the beam above. The maximum bending moment, what was it? It was 233.28 kip feet, right? That was the maximum bending moment in the beam. So our design bending moment was 233.28 kip feet. Now, what's a common strength for steel? You guys remember from your packets, let's say this is A992 steel. What I want you guys to do is determine the minimum size W shape needed to support the load. Let me know when you guys want me to continue. Everyone ready? Giving you guys a few minutes. Just give me a thumbs up when you're all good. You're good. What? I mean, yeah. Well, I was going to walk through it. Just, yeah. So, yeah, let's just do it together. Just so that way I'm not, like, waiting on you guys. So, what is the yield strength of A992 steel? That's what we need to know. Yes. So 50 KSI. Next, we write out our equation. Sigma is equal to M over S. We can use this equation because W shapes are doubly symmetric about their cross sections, about the neutral axis. They're symmetric, which means we can just use this very simplified equation. What we know is the allowable stress. We know what the bending moment is, but we don't know the section modulus. So that's what we're trying to solve. So we can rewrite our equation to be M over sigma. And then we just plug it in. 233.28 kip feet times 12 inches per foot, because we want our units to be consistent, divided by 50 kips per square inch. And what we get is that we need a section modulus of around 55.99 inches cubed. So let's say around 56 cubic inches. So, really quickly, just take a look at your design tables. Are we designing this for bending about the major axis or minor axis? Which value would you guys use, IX or IY, for the design of a W shape? IX, yeah. Most W shapes, you want them to be installed with the flanges top and bottom, which means you're using IX. So just take a few minutes, take a look at your W shape table, and just provide me with a size for the W shape that you guys would want to use. I'm getting way too many notifications. Turn off. I see something that works. I'm not gonna, yes,
Are we looking at like S of X to find the minimum like size?
exactly. You want to use S of X. Because if you were using SY, you would use if your W shape was basically being installed like this. Do you want your W shapes to be installed like that? Absolutely not. In very rare circumstances are they installed like this. The only thing that immediately comes to mind is like lagging for like retaining walls. And then generally you might have some type of like strut here. But other than that, no. For building systems, you want your W shapes to be oriented the other way. So just use the IX, IY values and just pay close attention to the orientation. Note, there isn't exactly a exact value for you guys to use, but as long as it's a reasonable value, it's a correct answer. So I'm not exactly looking for the smallest size W shape, but I am looking for an economical size. Like if you chose something like a W12 by 96, which is clearly more than double what we need, I would take points off because you're wasting money at that point.
Wasting money or being really safe?
What?
Wasting money or being really safe?
Yeah, but
Just saying.
if you were wasting money,
It's perspective. You don't know. I mean, like, the trade center now is like overkill, but we have our reasons.
Yeah. I mean, a lot of times, like, a lot of the factors of safety that come into play, which I'm going to do in a second, I just want you guys to get comfortable with looking at the table right now and picking the minimum size shape. The factors of safety are accounted for. So a lot of times, like, you know, the building code is usually like the minimum governing code.
Let's use the W10 by 51.
A W10 by 54, that's an option. Which gave us an SX value of 60 cubic inches. So that works. What other shapes? Anybody come up with anything else? A W12 by 50. All right, that's good. Any other values that anybody wants to share, even from the other tables? Yeah, Olivia.
W18 by 35.
W18 by 35. Which gives us a section modulus of 57.6 inches cubed. Yeah. They're all good because they're all greater than 56. What's the most economical? Why?
Because it's the closest to 56?
Well, not...
Or do you want mid-grade and you want to go...
Well, here's the thing. The W12 by 50 is actually even more economical than the W10 by 54. Why do you guys think that? The weight per unit foot is less, which means less steel. And then the W18 by 35 is better than both of them because it's a smaller weight per unit foot and it has a lower section modulus. So the lighter, the more economical.
You beat me.
All right. Now, what if we had a factor of safety of 2? Then our section modulus that we would need would become 56 times 2, so 112 cubic inches. In that case, what would be a W shape we would want to use? A W12 by by 96 gives us SX of 131 cubic inches. What else? W10 by 112 gives us 126 cubic inches.
W14 by 82.
A W what?
14 by 82.
Which is SX equals 123. Yeah. Now you guys know how to design steel beams. Any questions about this? All right. Now, here is your... I'll do one more example, because I think your get out of jail should be pretty straightforward, I think. This example is going to use the tables I gave you guys. All right? Let's say that we have a beam, a pin on the left-hand side, and a roller on the right-hand side. And let's say that there is a uniformly distributed load cut across and then a point load in the middle. Let's say that this is 5 kips and then 1 kip per foot, and then the total length of this beam is 10 feet. Now, you guys learned how to draw the shear and bending moment diagrams. You guys will need to do that for relatively complicated loading that are not provided in these tables. But this table here, this loading here, I think is simple enough just to be able to use these tables. So, what do you guys think? Think we can use any of the tables? Are there anything in here that allow us to be able to design with the tables at all, instead of having to draw the shear force and bending moment diagrams?
Did you use figure 1?
Figure 1 seems logical, but the only issue is you're forgetting about the point load in the middle. Anybody see any values in the table that could help us? No? Well, Michael was onto something. We can actually break up the loads into two separate figures and then sum the results together. So, what was the first figure you said? Figure 1, right?
Yeah.
So we could use figure 1 for the distributed load. Where was the maximum bending moment?
And the center.
Great. Now, I forgot to mention, the point load is also supposed to be at the center. Now, what about the point load? How do we handle the point load? Any figures in here for the point load? Yeah. Now, where is M max for this? It's at the center, right? Now, because the maximum bending moments in both instances are at the center, we can say that M max is equal to the bending moments summed together, which would be WL squared over 8 plus PL over 4. Which, when you plug these in, 1 kip per foot times the length is going to be the full length of the beam, 10 feet, squared divided by 8 plus 5 kips times 10 feet divided by 4. When you do the math, we get 25 kip feet. And so, if you were to draw the bending moment diagram, you would find that the maximum bending moment at the location is 25 kip feet. What if instead of it looking like this, I gave you guys something more along the lines. Come on, paste. This, where now this load here is 2.5 feet from that point. What do you guys think we would do from there? We could still use figure 1 for the distributed load, right? But what about the point load?
Use a figure 8.
Figure 8. Great. Where does M max occur for figure 1, for the distributed load? at the center. But what about at the point load?
Would it be with the load, like the point of load?
Exactly. It says right there, at point of load. Now, do the center of the beam and the point load coincide with each other? Do the M maxes align at the same position? No. So because of that, you need to calculate the maximum bending moment at two separate locations. Those two locations are going to be where an anticipated maximum bending moment will occur here and where a maximum bending moment will occur here. Let's call these points 1 and point 2. Does that make sense why we're doing that? Because the maximum bending moments, their locations don't align. So you need to check both and actually compare and contrast the two. This is just an easier or a faster way of doing the calculations than drawing the shear force and bending moment diagrams, because the way the 2 points that we're about to calculate for, you would get those same exact values as if you had drawn the diagrams. So let's look at point 1. Let's call it M1. How would we calculate M1? For figure 1, how would we do it? Simply put, we would want to calculate using that value mx that you guys see on the figure right there. That's just the bending moment at a particular point. Remember, we had, in previous lectures, I had showed you guys how to calculate those bending moment equations. If you guys look back at your previous lectures or haven't watched it yet, I show you guys how to derive those equations. These are just the equations given to you straight up for each load independently. So, for the distributed load, we can just use the Wx divided by 2 times L minus x. But what is x going to be? It's going to be the 2.5 feet. So let's plug it in. 1 kip per foot times 2.5 feet divided by 2 times 10 feet minus 2.5 feet. And that's for the distributed load. And then to add to that, we use figure 8. And again, we know that the maximum bending moment occurs at the location of the point load. So we can just use the PAB divided by L. Does that make sense? You could also use the MX equation and then plug in the variables accordingly, but you should get the same answer since the MX would be at the location of the point load. So you should get the same answer. Does that make sense? So our point load now becomes 5 kips times A, which is 2.5 feet, times B, which is going to be 7.5 feet, divided by the total length of 10 feet. And this is for the point load. So the bending moment at point 1, let me do the checks really quickly. We get 18.75 kip feet. Let's do it for M2 now. Are there any questions about how we get M1? And why we're using the equations we're using, or is those all clear? Yes?
For figure 8, what is x supposed to be?
X is the point of interest. So when we did like the section of cuts through the beam, X is that position with respect to where we're interested in. They just happen to do it differently, where X is just the position from the far left side of the beam. Whereas when I had done the derivations in class, I chose an X1 and an X2. They have the equations written as X for the entire length of the beam. Does that make sense?
So how would you use that one for this?
For M2 or M1?
The second one.
For M2.
Yeah.
All right. For M2, well, for the distributed load, we fortunately know that M max is at the center. That's our second point of interest. So we can just use the WL squared over 8 times 10 feet squared divided by 8. That's the distributed load, since the point is at the center. But for the point load now in figure 8, what we need to do when x is less than b. That is a good point. X is less than b. Yeah, it doesn't give it. Like I said, the tables are not perfect for everything. Yeah. I believe the way that this would be done. Here, let's look it up, because you can find like a lot of these also online if it just wants to. All right, that says when x is less than. And I believe that's a typo on your figure anyways, actually. So you see when it's where it says when x is less than b, that should be when x is less than a. So make that correction really quick. Yeah, that's a...
On the first page, it says horizontal distance from reaction to point on B, but would it just be the distance?
Right, but it looks like it's only giving you when x is less than... It's only, the equation is applicable only for a certain point. So... I guess in this case, let me try something. So P was 5 kips. What is M max at that point? So that's 5 times 2.5 times 7.5 divided by 10, which gives us 9.375. And then minus V2, which is going to be 5 times A divided by L. And then that distance is going to be 2.5. Okay. Yeah. So in that case, It looks like for this, you can still just plug in. Yeah. So you would just replace B and A from the looks of it. So for this, it would be 5 kips. And then for B, you would need to replace that with your A value, which would be 2.5 feet. X would be 5 feet. And then you divide that by 10 feet. I just did the math to double check using like the area method that I've been showing you guys, and so that it works. So you could just replace A and B with each other.
Wait, so where's the 5 feet from?
The 5 feet is X in that case. So then that B value, you would just replace that with A. It's a bit confusing, but it's just due to the symmetry of the problem. And what this gives you, 1 times 10 squared divided by 8 plus 5 times 2.5 times 5 divided by 10. This gives us, again, 18.75 kip feet. So I would ask you guys, what value do you use for the design? But ironically, they're the same value. So, yeah. Yeah, that to me looks like it would be that max bending would occur somewhere between 0.1 and 0.2. All right, time for your get out of jail. I'm kidding. I'm not going to hold you guys any longer. Yeah, you guys get lucky today. So yeah, that just kind of shows you guys there's the tables can help, but they don't solve every problem. You know, you can't just use them to get out of every single problem I give you guys. The best thing you can do is understand how the shear force and bending moment diagrams work. Any questions? All right.
Have a good night.
You as well.